Mute.
Perfect.
Okay. Hello everyone. Today we have the pleasure to welcome Gabriela Castelletti, who is a specialist of radio observation of supernova remnants and interaction with the ISM. She is here at the lab for 10 days visiting us, working with the AHE group, the Gamma Ray group. And so today she will present her work on the radio supernova remnants.
Okay, yes. Thank you very much for the introduction. It's a pleasure for me to be here and share with you two topics I'm passionate about, supernova remnants and radio observations. Well, I come from Buenos Aires City in Argentina, where I conduct my research with alongside a colleague. I have listed here some of them, which are associated with the results that I am presented today. Okay, the objects we are interested in are the aftermaths of stellar explosions. They can be produced by either the core collapse of massive star. The name of this object is supernova remnants, of course. Also, we have thermonuclear explosion from white dwarf in closed binary systems. Despite the mechanisms to produce supernova remnants, these both kinds of supernova are highly energetic and released to the into the interstellar medium from one solar masses of matter, or maybe four solar masses of matter traveling at 10,000 kilometers per second. Please, in what follows, keep in mind that supernova remnants consist of a forward shock created by the supersonic expansion of the stellar material ejected by the supernova, the stellar material itself, and if the progenitor star was a massive star, so we have ultra-dense compact object that sometimes we can observe as a pulsar. Well, to give a few a first view on supernova remnants, I think it's helpful to review the evolutionary status of these sources. If you consider a toy model in which the remnant is a sphere expanding outward, so we can divide the evolution of supernova remnants into four different phases. The initial phase is, in this initial phase, the conditions are given by the ejecta material from the supernova. During all this phase, the material of the sweep-up gas is much smaller than the mass of the ejecta. During this phase, the supernova remnant is strong, is intense, and expands freely into the interstellar medium. As the ejecta collide the shocked interstellar medium, so reverse shock begins to propagate into the ejecta, hitting it, and marking the transition to the second phase. As the forward shock propagates, it compresses the interstellar medium, hitting it adiabatically. The term adiabatic is used to indicate that in the sweep-up material, the radiative losses are minimal. So the internal energy of the remnant is transferred to the sweep-up gas. During this phase, the remnant will become major. Then, as time progresses, the velocity of the shocks decreases, and cooling processes behind the forward shock becomes significant, and radiation begins to dominate the evolution of the remnant. Eventually, only the ghost of the remnant remains, once strong and luminous At this phase, the supernova remnant it's now dim, up to the point of being so too fine to be observed. Okay, at the end of the evolution, the remnant merges with the interstellar medium, and these sources release the last breath of energy. But things rarely are unfold as we model. Take, for instance, this source. This beautiful remnant is, the name is Cassiopeia A. In this, this is the remnant of the destroyed star 340 years ago. Blue color here indicate the position of the forward shock, in this case emitting in X-ray, synchrotron X-ray, and the ejector is illuminated by silicon and iron lines. This feature here, we know this feature as the green monster, was recently, 1 year ago, detected by the James Webb telescope. This feature is in the debris of the star. It represents infrared emission from dust that is embedded in the X-ray hot emitting gas in the ejector. The forward shock, I think, is the reverse shock, I think is the most elusive component of a supernova remnant. The position of the reverse shock is approximately here, and notably, the first evidence pinpointing the position of the reverse shock came 20 years ago, approximately, from radio observations, especially from low radio frequency of absorption, a topic that we will see later during this talk. Okay. Beyond the evolutionary status of the supernova remnant, these sources are important because they can inform on a variety of subjects. Some of them are listed here, but as you can see, these topics cover different spatial scales from properties of the supernova progenitor to galaxy formation. And in radio, the tool that we have for studying these objects are imaging, polarization analysis, integrated and local spectra. The point is, a supernova remnant, in fact, emits across the whole electromagnetic spectrum, from radio to gamma rays. And take, for instance, this beautiful source, this iconic Graf nebula. This is the remnant of a star that Chinese astronomers observed for the first time in 1054. At the center of this nebula is an ultra-dense neutron star that is a dynamo of magnetic fields, intense magnetic fields, and radiation that can energize all the remnant. And here is this the emission, the 3 GHz emission from synchrotron relativistic electrons from the pulsar that are injected into the nebula. This is an image obtained with the Very Large Array. This is the image of the infrared emission from the Graf nebula. In fact, from dust that is absorbing the ultraviolet and visible light, and then radiate in infrared. This very complex network of filaments correspond to the optical emission in the graph, and we have also observed, we can also observe energetic electrons in ultraviolet and X-ray emission as well. Okay, the Graf nebula was also observed by the James Webb. This is the image from the James Webb in infrared, and all these different emissions, multi-wavelength information can inform about the dynamics and the morphology and energy radiation in the graph. So the question is, what do radio observation indicate? This is a mosaic with different supernova remnants emitting in radio wavelengths. At present, we know only 300 supernova remnants in our galaxy. Most of them were discovered in radio wavelengths. When we say radio emission from supernova remnants, we are talking about emission, synchrotron emission from electrons that are accelerated into the forward shock of the remnant. These particles follows power law energy spectrum, where this represents the number of particles per unit volume with different direction of motions. Synchrotron emission implies magnetic field, so polarization studies are useful tool for analyzing the magnetic field configurations in a few hundred parsec scale around the remnant. Well, in fact, the configuration of the magnetic fields with the ambient density are the main factors shaping the morphology of the supernova remnants, at least at radio wavelengths. At other wavelengths, for instance, optical or X-rays, the properties of the stellar explosion can influence the appearance of the remnant. Indeed, chemical composition, variations in the chemical composition across the face of the supernova remnant can affect the brightness at these wavelengths. The simulation that I am presenting here is demonstrate that for a remnant, the radio emission of the remnant expanding into the interstellar medium, the density strongly affect the morphology of the source. This is because the remnants expand more rapidly in low density regions. These produce asymmetries that increase over time. Okay, in relation to the environment, it is notable that probably around 80 supernova remnants show evidence for interactions with molecular cloud. This evidence can, for instance, from maser emission, CO emission, molecular hydrogen emission, and gamma rays as well. Talking about the magnetic field, in supernova remnant we can observe two configurations: radial of tangential geometries for the magnetic field. Of course, there are sources that present both configurations, and it's very difficult to distinguish between them. But the radial configuration is often observed in young supernova remnants, while the tangential configurations are most commonly observed in old sources. The explanation is that turbulence selectively amplify the radial component of the magnetic field, and as the shock front expands, well, the magnetic field is compressed, and the magnetic field transitions to the tangential geometry. Okay, the point is, maybe the important point is that regions with high intensity magnetic field are always associated with brightness radio emission, but the highest feature in radio emission, contributing to the appearance of bright limbs. For all sources, the degree of polarization is greater than that observed in young sources, and since the magnetic field is associated with morphologies, Probably the most challenging morphology to explain is the bilateral morphology, characterized by an axis of symmetry with two bright arcs separated by a region of low surface brightness in radio. Two configurations were proposed to explain this morphology: quasi-parallel and quasi-perpendicular morphologies of the magnetic field relative to the position of the normal shock. I think that the best example to explain this morphology is this source, the name is 296 plus 10. In this case, both morphologies, magnetic field configurations were proposed to explain the radio emission of this remnant. A first group of authors, based on a quasi-perpendicular magnetic field, explained the morphology of this source, taking into account the magnetic field, or taking into account the evolution of the remnant into a turbulent medium, and they considered a gradient either in the magnetic field or in the ambient density. More recently, these authors have put in place the progenitor star, and their magnetohydrodynamic and hydrodynamic simulations demonstrated that the radio morphology and the polarization pattern in this source can be explained by a quasi-parallel B-field configuration. In this case, the remnant is expanding into the magnetic field created by a red supergiant progenitor, and plus magnetic field uniform in the galaxy. Okay, even when this is a work in progress, I would like to show you this image. The case is the Pulsar Wind Nebula 3C58. This is an image, again, taken with the DLA. Represent the synchrotron emission from electrons emitting from 4 to 8 gigahertz. The pulsar is located approximately here, and the complex morphology of this source results from an interplay between among the pulsar, the fast particle wind, and the ejecta from the supernova. Okay, this source is similar to the Graph Nebula in the sense that no evidence of a forward shock has been found so far. The magnetic field in this Pulsar Wind Nebula looks like here, and as you can see, the magnetic field closely follows the brightness distribution. In fact, the highest brightness regions in the nebula. Well, one important tool that we have for analyzing supernova remnants is the spectral behavior. I mean that is the relationship between the flux density and the frequency emission of the electrons populations that are spiraling different configurations of the magnetic field. Supernova remnants spectra either taken integrating over the whole extension of the source or in local regions across the face of the source can inform on different topics. For instance, the energy distribution of the electrons can connect the low energy and high energy portions, radiations in the supernova remnants. They also can indicate information about the nebula around pulsars, because nebulae around pulsars have a flat spectral index. And maybe more important for this, in this context, spectral index analysis can also inform about the interaction of shock fronts with the interstellar medium. Typically, the supernova remnant radio spectrum follows a power law relationship, where the index of this distribution is related to the energy distribution of the particles and is shaped by the acceleration process in the supernova remnant. This table shows that there are both linear and non-linear models proposed to explain the reduction of energetic particles in supernova remnants and the radiation that we observe from them. Well, now I would like us to pay attention to the to the lowest frequency in radio spectrum. I mean frequencies below 100 megahertz. Despite the importance that low radio frequency observations have, the point is this part of the spectrum was historically limited by extremely poor angular resolution and sensitivity. Typically 1 order of magnitude or more worse than achieve a higher frequencies, gigahertz frequencies. Among all the studies that need low radio frequencies, that critically need low radio frequency observations, we will focus now in thermal absorption in on around supernova remnants. Indeed, supernova remnants are sensitive to ionized gas located anywhere along the line of sight. This ionized gas absorbs the emission that we observe from supernova remnants, and this ionized gas can dramatically impact on the supernova remnant spectra, as you can see here, producing a turnover below 100 megahertz. Okay, so modeling the flux density from supernova remnant with a component that is associated with the synchrotron emission from these sources, plus an exponential decay expressed in terms of the optical drift of the absorber at a reference frequency, can prove conditions on the ionized gas distributed in the galaxy. I mean electron temperature, electron density, or the size of this gas. As you can see here, there are 2 cases for the extrinsic absorption, because the much more common thermal absorption is extrinsic absorption, either by non-local or local gas. The non-local gas is associated with unrelated ionized gas. For instance, in H2 regions, distant H2 regions, or even in their envelopes. In other case, the local ionized gas is associated, for instance, with the interaction between supernova remnant shocks and the molecular cloud. I mean that the shocks is strong enough to impact the molecular cloud and ionize the gas. Other way to obtain a local absorption is by foreground H2 regions that are part of the same supernova remnant complex. Alternatively, we can find intrinsic absorption. This is observed in very, very young supernova remnants. In this case, the absorption is concentrated near the center of the supernova remnant, lying interior to the reverse shock. The ionized gas is in the cold and unshocked ejecta, which emits X-rays and infrared ionized gas in ionized lines. But this case was observed in, as I said earlier, in case A, Tycho, and in the Crab Nebula only. Okay, the construction of accurate radio continuum spectra requires to take into account several aspects. For instance, data quality, errors, the selection of an absolute flux density scale, and even frequency coverage that in some portion is oversampled, but in others could be partly studied. Now I would like to introduce a note regarding the similarity of the spectra. The point is that the use of a different reference frequency in this function, it has made it challenging to compare different supernova remnants or formulate a clear picture of the ionized gas in the galaxy. So I think it is beneficial to convert all the values to a common reference frequency, and to address this issue, we present this alternatively function for the flux density, which is written in terms of a characteristic flux density that normalizes the height of the spectrum, and a characteristic frequency, which is related to the spectral index of the synchrotron emission and the turnover frequency. This frequency is where the flux density reaches its maximum value. In other words, you can say that the characteristic frequency is parameterizing the degree of the absorption degree. I mean, the stronger the absorption, the higher the characteristic frequency. As you can see here, there are a variety of shapes for the spectra of supernova remnant, but all of them are well approximated by the new fitting function. Moreover, if you express the normalized flux as a function of a normalized frequency, so I think it's make evident the similarity between the spectrum. As you can see here, a higher frequency, in this case higher frequency is frequency higher than the characteristic frequency. All the spectra appear ordered, yeah, by the spectral index from the step to flat spectral index value. While at a lower frequency, all the spectra are well fit by a unique exponential drop-off. Although it is not shown here, I can say that the search for a correlation between radiation represented by alpha and radiation emission represented by alpha and absorption represented by this characteristic frequency indicates these two processes are independent. In other words, the absorption beyond the main boundaries of the contrary of the supernova remnant completely forgets the history and details of the acceleration process within the supernova remnant. Moreover, this new formulation can be used to derive the distribution of the ionized gas in the galaxy. Indeed, supernova remnant, whether presenting turnover spectra or no, seems to be distributed, well mixed in the galaxy without any evident segregation between them. Furthermore, the distribution of supernova remnants does not correlate with any general properties of the galaxy, for instance, the heliocentric distance, yes, or galactic longitudes. So, as we can expect, if the absorber could be distributed uniformly in the galaxy. On the contrary, the distribution of supernova remnants with and without turnover spectrum seems to be arise from absorbers that are discretely distributed in the galaxy. So the point is emission measures derived from galactic electron density models do not match observations. Well, let's go back to the interactions between shocks from and molecular clouds, I mean extrinsic thermal absorption. Here I present a handful of cases where this interaction was traced by the ionized gas in the interface of the impacted molecular cloud. I would like to emphasize at this moment that this tool, I mean the use of spectral index analysis, is useful even when the molecular data is not observable, because, for example, the molecular cloud is that, or because there are no molecular data available. With emerging low radio frequencies surveys, we can anticipate a big impact in this field. The new low radio frequency observations fill a portion of the spectrum that has been most poorly constrained by past measurements. Now, regarding the interaction between shocks with molecular clouds, I would like to say that shocks found in supernova remnants are efficient sites for particle acceleration. Through multiple scattering with magnetic turbulence, with each crossing, particles can gain a small amount of energy due to different velocity difference between the upstream pre-shock regions and downstream post-shock region. This incremental energy can result in significant energy for the particle, resulting in a power law distribution. This process is known as linear diffuse shock acceleration, sometimes called first Fermi order acceleration. A more complex version of this process incorporates the mutual influence between particles and the structure of the shock. In this new version, particles can amplify magnetic fields through instabilities that particles drive in themselves. The amplified magnetic field further enhances the acceleration efficiency, so the loop starts again, and again. In this updated version of the process, the energy distribution can deviate from the power law, simple power law predicted by the linear model, due to the enhance of the confinement of particles and due to the increased efficiency of the acceleration process. Anyway, all these processes that I am describing now collectively determine the spectral slope, the acceleration of efficiency, the maximum energy of the electrons, and the way in which the particles can escape from the shock region. Shocks impacted with molecular clouds can heat, can compress, and even ionize the molecular cloud. All of these processes can influence in the acceleration efficiency. Indeed, the increased density provide more target for the accelerated particles, and this can change the acceleration rates and the subsequent radiation from the supernova remnant. Moreover, the impact of the shock fronts into molecular clouds can amplify magnetic fields. We know that magnetic fields, when high magnetic fields, amplify and increase the acceleration process, and also provide higher energy photons that potentially can emit in synchrotron X-rays. This process, the interaction between shocks and molecular clouds, can also produce gamma rays. And the good news is radio observations can trace the impact, the interaction between the shocks and molecular clouds. And also radio observation can test the diffuse shock acceleration because the spectral index in radio is associated with the energy distribution of the electrons emitting synchrotron. Good. The number of supernova remnants emitting high energy light has progressively increased, demonstrating that these sources are capable of accelerating particles to multi-TeV energies. This fact links supernova remnants directly links supernova remnants with the origin of cosmic rays. However, the ultimate proof that the supernova remnant dominates the origin of hadronic rays is still remains, is not present. In this regard, I think gamma rays are relevant. Gamma rays observations are relevant because they can provide further evidence for this belief and also improve our understanding of the processes, the accelerations in shocks in supernova remnants. Here, there is a collection of gamma rays emission from supernova remnant with different ages and with evolution into different gamma ray interstellar medium context. From the theoretical point of view, even when the nonlinear process can increase the acceleration efficiency and also increase the maximum energy of the particles, there are still some issues that need more attention from our side. For instance, the nonlinear process alone does not fully explain why the high energy cutoff in cosmic rays. The maximum energy of the particles depend on several factors. For instance, the age of the remnant, the efficiency of the acceleration process, and the intensity of the magnetic field. Predictions based on the age of supernova remnants indicate that the maximum energy of particles decreases with the age of the remnant. Just to put some numbers, in very young sources or young sources, the maximum energy could be, the maximum energy of particles could be 100 TeV. I mean sources with a few hundred years or maybe a few thousand years old. For old supernova remnants, the maximum energy is around 10 TeV or even less. The explanation is that in young supernova remnant, the shock front is high, the intensity of the magnetic field is high as well, so this confines particles, and in a short time they can reach high energy before escaping of the shock region. While in all supernova remnants, the shock is slow, the magnetic field is weak, and particles can escape more easily without reach any high energy. Okay. When we say non-thermal emission from supernova remnant, we are talking about synchrotron emission that could be present by radio emission or X-ray. Indeed, TeV electrons can emit radio waves, TeV electrons can emit X-rays, and several 10 TeV electrons can emit in gamma rays due to inverse Compton scattering with CMB or infrared emission from stars. In dense regions, these electrons can also emit from soft X-ray to gamma rays through Bremsstrahlung process. Protons are different because protons are heavy particles, and so we cannot observe the radiation from these particles directly. Instead, we can observe gamma rays after the decay of neutron pions created by the hard collision between an accelerated protons and the interstellar medium. Since the intensity of this radiation is proportional to the ambient density and also to the flux of proton, we expect to observe hadronic gamma rays from regions, dense regions in the interstellar medium. The point is that when we observe gamma rays from an astrophysical object, identifying the parent particle, I mean electrons or protons, is crucial to understand which is the physical process that dominates. In this regard, radio observations are useful because they can help because they anchor the low energy portion of the spectrum, which otherwise could be incorrectly extrapolated from higher energy data. As we said, also gamma radio waves can trace shock acceleration particles. This is this shock acceleration because they can test diffuse shock acceleration models, and radio observations can also identify interaction between shock fronts and molecular clouds. This is important in order to understand hadronic gamma rays. Radio observation can directly observe dense regions in the interstellar medium, dense targets, or can identify the ionized gas created by the impact of the shocks with molecular clouds. Well, finally, I would like to present, or I would like to announce that we are actively compiling a comprehensive Supernova Remnants radio continuum to make a catalog. We hope that this new resource will soon be available to everyone, and the idea is our new catalog facilitates deeper insights to cover all the topics that I showed in this talk. Summing up, Supernova Remnant radio imaging and spectral analysis inform on ambient magnetic field configuration, thermal and non-thermal components in complex lines of sight. In this violet bullet is the similarity of the radio spectra. Also can provide information on interaction between homogeneous and clumpy clouds and cosmic ray acceleration. Okay, so thank you very much for your attention. Thanks.
Just a very simple question. What is the kind of magnitude of this magnetic field you were talking about?
Well, yes, good question. The magnetic field depends on if you are talking radio emission, is microgauss. The magnetic field is always amplified, yes, by the acceleration process. In the case of synchrotron X-ray emission, the magnetic field could be milligauss. Yes? But synchrotron emission and in X-rays was observed only in approximately 20 supernova remnants, but in our galaxy they are 300, yes, supernova remnants. These 20 supernova remnants with synchrotron X-ray emissions are very young sources.
So it's very small.
Mm-hmm. Yes.
Yeah, I have a question. If you go back to your self-similar distribution of radio spectra,
yeah.
What is the distribution of alpha values telling us about?
You say about the synchrotron radio emission?
Yes, exactly.
Okay. Alpha goes from approximately minus 0.3 up to 0.7, minus 0.7. in the simple scenario, the standard approach is that more steep is the value of alpha. You are referring to supernova remnant that is old, yes? But this is in the standard scenario because we know that there is there are cases where the alpha value is steep, but they are supernova remnant young. Okay, but the range is minus 0.3 to minus 0.7, 0.8.
Okay, and then so my question is, the fact that we have some kind of envelope, that we have values that we cannot go beyond,
Okay, yeah.
is it coming from some primary acceleration? Process is something that is linked to the way that electrons are accelerated.
Electrons are always accelerated in supernova remnant, but when we see a turnover, the presence of the turnover does not affect the synchrotron emission.
Right.
That does not change the synchrotron emission, does not change the spectral index. Is it okay?
No. Can you show that? Maybe if you show the image, it's clearer.
Yeah.
So my question is, there is clearly a range of values of that.
Yeah.
And so they cannot be flatter than a given value. So the fact that all the indexes really seems to kind of be limited or constrained by some kind of value. What is it? Okay, if you show the image,
Yep.
I will reformulate it.
I think that I can go
Yes,
this image
yeah,
or
okay,
this one.
yes. So my question is, why don't we have hardware spectrum? So why the
Hardware
hardware
is flat.
Flat, yes.
Hardware for
Same,
gamma
it's
is flat in
Yes.
radial, yeah?
Why don't we have something flatter than red?
Well, we have flat values, flat spectral values, but the flattest is minus 0.3. We don't know see that values flatter than this value in supernova remnants. Probably only in pulsar wind nebula, because so more energetic is the source, flatter is the spectrum, you know. But the flatter value, for instance, minus 0.1 or approximately 0 correspond to A2 regions, not supernova remnants. Supernova remnants always have a spectral index that are steep than minus 0.1. Yeah? Yes?
Yeah, I have a sort of basic question about the shocks. So if you have, look at the setup solution, you just have a single outgoing shock. Do the reverse shocks come from inhomogeneities and what's around the exploding supernova? Or
Okay.
how does one determine where the reverse shocks start?
I think the answer is when the ejector is moving at a supersonic motion, and in this way it's created the shock storm. Yes, but I'm sure if I understand very well your question.
Well, I mean, you were saying that there's a forward shock.
Yes.
And then there are shocks that propagate in the opposite
The reverse.
direction. Yeah.
You are talking about the reverse shock.
Yes, yes.
Ah, okay. So the reverse shock forms when the ejector collides the shock material by the forward shock. In other words, you can say that the reverse shock knows about the interaction of the forward shock with the interstellar medium. You know? This is your question about the reverse shock. How is the expansion of the reverse shock into the ejector?
So it's sort of a reflection of the forward
It's
shock.
not exactly a reflection. It's not exactly a reflection. Yes, it's something that happened with in the discontinuity between the matter shock by the forward shock and the ejector, but it's not exactly a reflection.
Okay, thanks.
Reflection is more complex because when you say reflection, they are reflections in the form. That's that. From this reflection, does not result the real shock. It's a little more complex situation.
When you talk about mapping the ionized gas in the galaxy with this absorption feature in the spectra of SNR, how do you attribute distance to this? How you know if it's due to, I don't know, ionization close to the SNR or in somewhere in the field of view?
Okay, the first things I should to say is that when you talk about extrinsic absorption, in fact, the spectral index or the turnovers in the spectral have no information about the distance, the relative distance between the absorber and the emitter. Yeah? But if you take a different distance to the supernova remnant, you can say that they are well mixed in the galaxy with and without turnover. So if you suppose that the ionized gas is continuously distributed in the galaxy, well, you have to observe supernova remnant with more pronounced turnover with the distance, but this is not the case. And the distance for each of the supernova remnant was derived from, for instance, for example, from H1 absorption and any other process. Yeah, this is a good point, because you say that these spectral turnovers, of course, correspond to absorption, extrinsic absorption, but in fact, you know nothing about the relative distance between the absorber and the emitter. But when the absorption is extrinsic, right, you are in the local case, result the optical depth is higher than in the case of the non-local case of absorption. Yes, because envelopes around normal A2 regions have low density, and if you are talking of ionized gas in the interface in the ionized interface, yes. The size of the ionized region is small, but the density is not. And as a consequence, the optical depth in this case is higher. Yes?
Is it possible that there is an annihilation part in the spectrum?
Sorry? The annihilation?
Is it possible that there is an annihilation part in the spectrum?
Into parts? Into different parts of the spectrum, you say?
No, like electrons and positrons that make annihilation.
No. Okay. No, I don't think so.
Basic question. So you mentioned at the very beginning that the supernova remnant, it causes local compression of the interstellar medium. Does this local compression triggers star formation processes? Or
No. Some people say that yes, but I think no. Anyway, the supernova remnant, we can prove your point. Yes, there is no proof about the supernova remnant triggering star formation. But I could say that the expansion of the forward shock into turbulence interstellar medium can increase this turbulence, and the consequence of this maybe